In this talk, I will present a new framework of tree-to-tree transformations. We call it Linear High-Order Deterministic Tree Transducer with regular look-ahead. I will also present a more general variant of this model, which is almost linear instead of linear. I will start by giving a brief state-of-the-art of the already existing model of tree transductions. Then I will define our models, and then I will present the results we have on our new model of transducers. First, I will show that it is equivalent to known models. Then I will explain how we can compute the composition of two linear transducers. And finally, I will explain how we can reduce the order of a transducer that is either linear or almost linear. The model that interests us as point of comparison against our model are these four. Deterministic top-down tree transducers are quite simple. Monadic second-order logic transducers are a bit more complicated, although they lack power of copying subtrees, I would say. I will talk more about it later. We also have attribute tree transducers and macro tree transducers. The expressivity of these models are all comparable, and so MTTs are strictly more expressive than ATTs. ATTs are strictly more expressive than MSOT transducers, etc. There exist some models that improve the expressive power of MSO transducers. There are also models that reduce the copying power of ATTs and MTTs, and that makes them as expressive as MSO transducer. These are called single-use restricted ATTs and finite copying MTTs. The MSO transducer model with unfolding works like this. So first you use an MSO formula to transform a tree into a tree with sharing. That is a tree where a subtree can be twice the child of other nodes in the tree, and then you unfold the tree with sharing to get a regular tree, and this increases the power of copy of MSO, because without this unfolding of trees, the size of the output of an MSO transduction is bounded linearly by the size of the input, and this can be a problem sometimes. It restricts the expressivity of the MSO model. Then I will introduce a few things before I can get to our new models of linear and almost linear transducers. First, I will go over some lambda calculus notions. We use simply typed lambda calculus, so we have atomic types and functional types built on atomic types. We compute the order in a very normal way. It is the usual way to compute order, and but it is important for what we'll talk about later. We use tree signatures So a tree signature is composed of an atomic type, a set of constants, and a typing function that gives types to these constants. The constant represent the labels you can have on a ranked tree. So each constant has a type which corresponds to the arity of the label it represents. For example, if you have a label F of arity 2 and a label G of arity 0, the constants that correspond to these labels will have type O2 to O for F and O for G. And so a tree that is represented like this can be represented as a lambda term like this. I will also explain how regular look-ahead works. So it's bottom-up tree automaton without any final states, set of final states. It is run before the transducer is actually starts the top-down computation, and it labels each node with a state from the bottom-up tree automaton. And these states will be read by the transducer, and the transducer will be able to do different things depending on what the look-ahead tells it. The transducer in general has different input tree signature and output tree signature. The state signature is important because this will tell you what the order of the transducer is. The order of the transducer will be the maximum order of one of its states, and the order of states is the order of their output type. Each state has a fixed output type, which is like this, with a queue built only on the output type. So once a queue is given an input tree, it doesn't work with input trees anymore. This is very useful because it ensures that you don't apply a state to something that has already been processed. The rules of the transducer are like this. So this is normal. This is the label of the current node, and these represent the child nodes of this node. These are the look-ahead states that have been computed by the look-ahead automaton. You have one for each of the child trees. And the output of each rule is a term that is linear in the case we have a linear transducer, and almost linear in the case we have an almost linear transducer. We'll show how this works on an example. Before we get to the example though, let me tell you about linearity. A lambda term is linear when each variable is used exactly once in each term. This is important because that means that you can't copy anything, and that's why this model will be shown to be equivalent to MSO without unfolding. And almost linearity is a bit different in that we allow for variables of atomic type, that is output trees, the type of output trees, to be copied, but not the variables of higher order. So as an example, we will try to compute the addition by coding numbers with trees. So we have a successor function, successor constant of arity1, like this, and 0 constant of arity0. And so you can represent the number 1 like this and the number 3 like this. We have an output tree signature that is a bit different because it is important to differentiate the input and the output type. And so, for example, if we have this input tree, we want our transducer to output this, which represents the number 3. The rules of the transducer really just reproduce the ways lambda calculus usually computes the addition. And we don't use any look-ahead automaton. It is not necessary in this case. So we just have one look-ahead state, and it doesn't change anything to the processing of the transducer. When we make this work on the example we gave earlier, so when we add 2 and 1, so this transducer works by reduction. So at each step you can reduce either by using a rule from the transducer or by using a beta reduction, which is available when you have lambda abstractions and application of those. The order in which you reduce is not important. You can start by reducing all the rules of the transducer, and this will eliminate the states in the expression, and then do all the beta reduction. Or you can do like this, using beta reduction as soon as the redox appears. Either way you get the same result. It is reduction is confluent, so you always get the same result. This way of computing is interesting in how it compares to existing models. So what you can see is that if you remove the part about the regular look-ahead, then the structure of rules of our model is very similar to the rules of DTOPS and MTTs. The only difference is that on DTOPS the term is always of order 0, and that is interesting because it means that our model generalizes DTOPS, and it is also the case for MTTs, except this time with terms of order 0 or 1. We have seen earlier that MTTs are more expressive than monadic second-order logic, and that's because of their copying power, and that's why we use this constraint of linearity, because it makes things a lot simpler, and among other things, it allows the set of transductions we represent to be closed by composition. So it's interesting. We'll see now that the linear model is equivalent to the MSO transduction model and the single-use restricted attribute tree transducer model. The almost linear variant is equivalent to ATTs and MSO transductions with unfolding of trees. And just as I said earlier, the copying power of almost linear is more than that of linear transducer, and that means in this case that almost linear transducer are not closed by composition. So in comparison to other model, we have this. So all of these models are equivalent, and all of these are equivalent in terms of expressivity. We'll now see how we can compute the composition of two transducers that are linear. As I said, the almost linear model is not closed under composition, so it would be possible. So given two transducers, we try to compute a new transducer that does the composition of the two. For this, we use things from the lambda calculus toolbox. More specifically, we use denotation semantics and coherence spaces defined by Jean-Yves Girard. The algorithm of composition has very good complexity. It is doubly exponential in the input. It is it is better than the non-elementary complexity of other algorithm of composition for equivalent models, except for the MSO transducer model, because, well, it is simply exponential. That there's an algorithm that is simply exponential to compute composition of two MSO transducers. But we think that our algorithm is still relevant because MSO is a model that doesn't attempt to reproduce the behavior of program, and any attempt at transforming an MSO formula into any other kind of transducer is bound to increase a lot the size of the transducer, and that lowers a lot the efficiency of composition in this model, in the MSO model. With this model, since it generalizes a lot of existing models, it is possible to translate other transducer from other models into our model and then use this algorithm of composition. And there is a gain in complexity when we do composition in our model, even if we take into account the fact that it takes some time to translate between two models. Next, I will talk about the reduction of order. This is a really important part of the paper because it allows us to show that the model is equivalent to other models. Without this, it would be really hard to compute computations of higher order into simpler models. The idea behind this is that each lambda term that is computed by a state of the transducer can be decomposed into a set of tree contexts that contain all the constant from the tree signature. So all the things that are pieces of trees, and then a template which tells us how these are put together to build the term. It's simpler to see on an example. So, for example, with this term m, with two variables y1 of type O to O and y2 of type O, we can write it this way, and it's important to write it this way, because what we see is that we have groups of nodes that we can piece together and create tree context with these, and then we will have a template that uses the tree context to build the term m. So this is the template, and we replace each of the tree context with a new fresh variable, and we isolate the tree context. Tree context are trees with variables of atomic types. This is important because it means that tree contexts are of order 1, and we'll see that order is important when we want to reduce the order, of course. What we'll see is that for each type, there's a finitely many templates you can have for the terms of that type. So we saw earlier that our term had this type. Well, for linear terms, either you have this type, you have this template, or you have this template. There is no other way. And if you use almost linear templates, you have one more template that is possible, which is it is copying the variable y2, which is of atomic type. And since we have to use every variable, these are the only templates you can have for terms of that type. So in general, for any type, this works. And it's really important because this allows us to put the information of templates into the finite state structure of the transducer. And so we can translate that transducer into a transducer that only computes the tree context. So the template is already remembered in the state, and at the end of each computation, the initial state of the transducer will put things together to produce the output tree. But the computation is just done like this, so it just computes tree context by putting tree context with other tree contexts, and the order of the transducer that only computes this is 3, because we use tuples of tree context, and using tuples raises the order by 2. We use continuation passing in order to emulate tuples. This means that we can reduce the order, and this is a crucial part of the proof that our models are equivalent to MSOT transducers. To conclude, I will say that we have defined a model that generalizes several existing models, and we have designed an efficient algorithm for composition, which also gives insight into how composition algorithm works for equivalent models. We think that the reduction of order that we do at the end of composition, if we want to translate our model into other models, is a step that is hidden in other algorithm for composition, and that is why we are confident that our model is a good generalization of other models. I will leave you with references. Thank you for your attention.